In this video, we're going to talk about how to find the area between two curves. And this is broken up into 3 different parts, and the difference between the parts is going to kind of be related to the difficulty of them or the complicatedness of them, if you want to think of it that way. So at this point, you should already know how to find a definite integral. Definite integrals are the integrals that have numbers on the side. So the integral from 0 to 2 of x squared dx or something like that would be a definite integral. And we also, at this point, hopefully know that if I find the answer to that, what I've actually found is the area underneath the curve x squared from an x value of 0 to an x value of 2. Now that we've got that established, we're going to add some complexity to it by saying, well, what if I'm not doing the area between a curve and the x-axis? What if I want to know the area between 2 curves? And remember that curves don't necessarily have to be curvy-like. And when we're talking in math about curves, they can be straight lines, and that's fine. But we're just saying that we have 2 different graphs. We want to find the area between them. So there's a formula that you can think of for that, that A for area equals, and we're going to go from A to B, which A and B are either going to be given to us in some way, or we're going to get those from our graphs. It depends on how complicated our problem is. But inside of our integral, because we're trying to use 2 different functions to find this area, we're going to take our functions and subtract them. But the order is going to matter, just like it always matters when you're subtracting. F of x has to be the greater function, and by greater what we mean is that it would be the function that's above the other. And so this again can make things kind of complicated sometimes, because sometimes graphs cross and switch which one's higher than the other. Right now in this first part, we're just going to do some relatively easy ones so that we can practice using the formula, practice graphing, and remind ourselves how to integrate these definite integrals. So like in these examples, we'll know the boundaries already because they'll tell them to us. So let's take a look. On each of these examples, it says, for each problem, find the area of the region enclosed by the curves, use the provided graph to sketch the curves, and shade the enclosed region. Now, depending on how your teacher wants you to do this, or if you're in an AP calculus class or a regular calculus class, depends on how you would approach this. Like, you may not actually need to graph it to be able to figure it out, but a graph is helpful. Also, depending on your teacher, you may or may not need to know how to graph these by hand. So when I walk through this, I'm going to have my calculator to help me graph it, mostly just to make sure I graph it right, and because it takes too long whenever you plug things in if you're watching a video. But if you were doing it by hand, we would say, okay, these are both parabolas. The first one has a negative, so it's a parabola that opens down, and then we would think of points that we could plot in order to figure out what this looks like. And then we would do the same thing with the second one. This also opens down. If you're allowed to use your calculator, you'll just put in these 2 graphs into y equals, and then use your table of values to plot points. It is also helpful to look at your graph to make sure that your graph looks right, to make sure you're not missing out on something. And you may notice that I have a couple lines on here that you don't have on, because I tried to draw these lines by hand, and because I'm on a computer doing this, it did not look good at all. So we take first the x equals -2 and the x equals +2, and we draw vertical lines at -2 and +2. That means that everything on either side, on the left side or the right side, isn't going to matter to us. We might still graph some points out there so that we get a good idea of what our graph looks like, but the shaded region is going to have to be inside of those 2 lines. So I've put these into y equals on my calculator, and the first equation gives me points like -2, -6, so that's down here, gives me -1, 0, and then 0, 2, and then it starts going back down and we get 1, 0, which means I have to have 2, -6 also. And so maybe I'll draw parabolas better than I was drawing lines earlier. Not really, but it's okay. Pretend that that's a really cool, awesome parabola. Yeah, okay, so then our next one if we graph some points. And since it's negative 1/2, I put a negative 0.5 personally in front so I wouldn't have to make it a fraction. And so that means some of our points will be decimals, and that may make you uncomfortable, but it is what it is. We have -4, -4, and so we don't necessarily have to graph this point that's way out here, but we might as well. Then we get -3, -0.5, -2, 2, -1, 3.5, and 0, 4, which is the top, and then it'll go back down. One thing you can do with parabolas is, as long as you know where the vertex is, you can reflect your points onto either side. I'm doing a really bad job of this. Okay. We want to connect these. And make it look like a parabola. And then once we have them, these points went away on me. Drats. Once we've connected them, we're going to look at now what our basic shape is. What we want to do is find the area between these two parabolas and inside of our boundary lines, which means that we want to shade inside here. This is where we're finding the area of. And it does ask you in these instructions to shade the region you're trying to find the area of. So this is our figure that we're trying to find the area of. There's not any geometrical formula like that, which is one of the things that's so great about calculus, is that if when in geometry you were learning about area of circles and triangles and all this, if it ever occurred to you like, shouldn't there be a way that we can find the area of like anything? This is one way to do it. If you can make it into some mathematical function, which may or may not be difficult, then you can find the area like we're about to do. So our formula is that we have a equals our integral, and the numbers we use are the left side boundary and the right side boundary. So since they gave us x equals -2 and x equals +2, that is what our boundaries are. And then inside of our integral, we're going to take the top function minus the bottom function. So which of these was the top function? It's the green one on my graph, but was that the first function or the second function? And so if you don't remember, you'd need to go back and look on your calculator or whatever and figure that out. The top function is the one with the -1/2 because it's wider than the other one. And so we're going to put that function first, -x² over 2 plus 4. We're going to subtract the other function. And so that's why I'm putting these extra parentheses, is to show that I'm subtracting them. And the thing that is going to be easy to mess up, even if you get this far, is in order for us to actually figure out this integral, we're going to have to, we don't have to, but we should go ahead and distribute the negative so we can add like terms, because that's going to make us not have as much work to do. So whenever I distribute it, the first parentheses doesn't change, but the second one becomes +2x² and -2. And that may be something that you could do in your head, that you're just like, when I put this in, I'm going to change the signs because I'm subtracting. Now we want to do -x² over 2 plus 2x², because those are like terms. And so you may have to think about that kind of hard. This is -1/2 plus 2, which is 1.5 or 3/2 x². 4 and -2 come together to give us 2. And so this is our integral we're trying to find. We're going to find it using the power rule because these are both polynomials. So if I want to use the power rule on 3/2 x squared, you add a power, so that's going to make it be 3, and then we're going to divide by that power, which is 3. So that means this 3 and this 3 will cancel because 1 is on top, and then we're dividing by a 3, which would make it be on bottom, which means that this turns into 1/2 x squared. X cubed, I mean. 1/2 x cubed. We added a power to get cubed. We divided by 3, and that got rid of the 3 out of the 3/2. When I do the integral of plus 2, it doesn't have an x, so it gets an x. So that's plus 2x. And then what we're going to do is evaluate our integral at 2 and negative 2, which means we have to plug in each of these and then subtract our answers. So we're going to do 1/2 times 2 squared plus 2 times 2 minus, that was a cubed. I'm going to have to pay attention to that. You might have to as well. 1/2 and then negative 2 cubed plus 2 times negative 2. And we're going to work this out and see what we get. And again, it depends on your teacher. If you're allowed to use a calculator, you could type this into your calculator. If you're not supposed to be relying on a calculator, you'd do this by hand. You'd say 2 cubed is 8, 1/2 times 8 is 4, 2 times 2 is 4, so this first part is 8. Negative 2 cubed is negative 8, divided by 2 is negative 4. 2 times negative 2 is negative 4, so that gave us negative 8, but we are subtracting in between these. So if I do 8 minus a negative 8, I get 16. That's a really nice number. It doesn't always work out that nice, so a lot of times we end up with fractions as answers. So the area between those two curves is 16. There are a couple more examples of this, and so if you feel like you've got it at this point, you could go ahead and try to do it yourself. But on some of these next ones, we might have slightly different functions that we may or may not remember how to integrate right off the bat, or that we don't know how to graph right off the bat. So let's look at example 2. Speaking of things you may not know how to graph, we have square root functions, which square root functions are actually pretty easy to graph. I've already got the lines for x equals 0 and x equals 4, which you can put on there if you need to, especially the x equals 4 would be helpful so you know where to stop. Whenever I graph 3 times the square root of x, what that does is it starts at 0, 0, and then when you plug in 1 to the square root, you get 1, but you have to times it by 3. And then the next number we would plug in, or if you're looking at the table of values, the next number you would look at is when x is 4. You square root 4 and get 2. 2 times 3 is 6. So at 4, we should be at 6. And then after that, the next good number is 9, which is not on this graph, so I'm not going to worry about it. And so it looks kind of like this. That's our first one. So that was our green function. Let's see let's go with orange. What does orange look like? Again, we start at 0 for square roots. Unless we're adding or subtracting a number inside or outside, we'll start at 0, 0. This time when I plug in 1, I get 1 for the square root, but times it by 2 and get 2. And then when I plug in 4 and square root it, I get 2, but I times it by 2 and get 4. So again, I went ahead and kind of explained how to do that by hand, because like I said, I don't think it's super difficult to do that. If you're allowed to use your calculator, then by all means, graph it on your calculator. If you're not allowed, then you would want to obviously plug in points like what I just did. The area we want to find is between x is 0 and x is 4, and in between these two curves, so that's this area right here, which is a funny looking area, kind of. I guess all of these are going to be kind of funny looking, but that's okay. So that's the area we're trying to find. Let's set up our integral. They told us 0 and 4 for our boundaries, and we want to do the top function, which is our green function, so 3 square roots of x, minus our other function, 2 square roots of x. Now, both of those are fairly small functions. Like there's not a whole lot going on there except just the square root, which is nice because think about it. What is 3 square roots of x minus 2 square roots of x? That's like saying just 3x minus 2x would be 1x. So this will end up being simplified to 1 square root of x, or just square root of x. But it may have been a while since you've thought about integrating the square root of x. Let's remember how to do that. We want to change this to a power instead of a radical. So radicals give us fractional powers. If it's the square root, it would turn into x to the 1/2. And then once we know that it's x to the 1/2, we're going to use the power rule. So we're going to add a power and divide. When I add 1 to 1/2, I'm going to have to use common denominators. So 2 over 2, I do 1/2 plus 2 over 2 and get 3/2 for my power. And then I'm going to divide by 3/2. So we'll go ahead and clean that up a little bit. If I divide by 3/2 and there's nothing in front to divide by, what's going to happen is I'm going to multiply by the reciprocal. So I'm going to turn 3/2 upside down and make it be 2/3 x to the 3/2. The other thing about x to the 3/2 is, what is that actually telling us to do? It's actually telling us the bottom number is our root, so it's a square root. The top number is our power. And so it's really saying the square root of x cubed, or you could put that the other way where the cubed is underneath the square root, but this will be easier for us to do the math. And then we're going to plug in 4 and 0. So this gives me 2/3 square root of 4 cubed minus, and if you think about it, when you plug in 0, you'll get 0. So you can just put minus 0 there. We just need to figure this out. Your calculator will do it, but that's kind of the boring way of doing it, because you know the square root of 4 is 2, and we want to cube that, which gives you 8. So we want to do 2/3 times 8, which is 16/3. We'll do one more, and so again, I already have the lines drawn, and we're going to graph. Now these, one of these is not a weird looking function, but the other one is. Y equals 4, oh no, that's a straight line. Let me see how well I can do with this. I can't even find my cursor. Cursor, where are you? There we go. So y equals 2. That was way better than all the other lines I've drawn today, so it's in the wrong spot. So why did I even bother with this, is what I would like to know. All right, at 4. Oh, that line was so good. Okay, so then we want to graph y equals -4 over x squared, and it may have been a while since you've graphed a rational function like that. So you can plug it into your calculator, or you can pick numbers to plug in and see what happens. If we look at our table of values, we're going to see a lot of fractions. We're also going to see some errors, like there's an error at 0 because there's a vertical asymptote at 0. Then we'll just have to do our best to graph the other points we have. Like -1, -4 is a nice point, and -2, -1 is a nice point. But then we get decimals like -3, -0.4 repeating, and then it just keeps getting closer basically to 0. So what's happening, oh, that's not the direction that was supposed to go, is that it gets closer to 0, and then it gets closer to 0 coming this other way. Look at the graph on your calculator, because it looks so much better than this, I'm sure. We want to shade what's in between here, and there's another part to this graph over on this other side, but we don't need it because of where our region is. This is what we want to find the area of. So we have to say which one of these is on top, which one of them is on bottom. Our boundaries are -4 and -2. So we're going to do the top, which is 4, minus the bottom, which is -4 over x squared. So we're going to ching chang walla walla bing bang those negatives away, or whatever you learned in middle school, click click or change change or whatever. And then we can go ahead and integrate this. Maybe 4 gets an x. To integrate 4 over x squared, we have to think of that as 4x to negative 2. We add a power and get negative 1, and then divide by our power. And that gives us negative 4. We move the x back down to the bottom so it doesn't have a negative exponent anymore. We're going to plug in negative 2 and negative 4, and then we'll have our answer. So this is negative 8 plus 2 minus negative 16 plus 1, negative 6 minus a negative 15, so that'll be plus, and that gives us 9. So that's the area between those two curves.